Hello everyone, in this video we're going to be giving an intro to logic, quantifiers, and set theory. This is just going to be a brief overview so that you can understand what this notation means, as it's very common to show up in many math problems. Alright, so let's start with logic. So in logic we're comparing statements that can either be true or false, and looking at statements that combine multiple propositions. So let's take P and Q as propositions. These are statements that either can be true or false, so we'll make a truth table to see what these different operations mean. So P can either be true or false, and Q can either be true or false. So we can assign these values as true or false. And so since we have two of four different cases, I'm going to start with true. So we'll either have P being true and Q being true, P being true and Q being false, false true, and false false. And so these are all the different combinations, and we're going to look at what these mean. So first we have the not operator, which simply just means if it's true, then if P is true, then not P is false. And if P is false, then not P is true. So it's just going to be the opposite of P. So if P is true, we have false for both of these, and then when P is false, we have true. Okay? The and operator is saying P and Q. And so this is true when both P and Q are true, and false in every other situation. So in this first case, P is true and Q is true, so this operation will be true. But in every other case, we have a false, so everyone else will be false. So we have true and false, but since Q is false, we're going to get false. We have false and true, there's still one false, and even when they're both false, it's still going to be false. Okay? And now we have or, and this is saying P or Q. Okay? So when we have this or, it just means that either of them are true or both of them can be true. It's not an exclusive or, which you could define as a different operator if you wanted to. Okay, so in this first case, P is true and Q is true, so P or Q is still true. Now in this case, P is Q, and P is true and Q is false, so P or Q will be true. In this case, P is false but Q is true, so this one will still be true. And then this final case is the only case where it's false is when they're both false. Okay? And now we have this conditional statement saying if P, then Q. So if P is true, then Q must be true. But if P is false, we don't really care what Q is, because it's not even going to check Q, because if we say if the ground is wet, then it rained, if the ground isn't wet, then we don't care if it rained or not. It's just going to be a true statement because we're only checking if P is true. Okay, so we'll see how this works out in the truth table. And so we have if P then Q, so P is true, so now Q must be true for this statement to be true, and it is, so this one will be true. But now in this next statement it says P is true, but Q is false. But this says if P is true, then Q must be true. But since Q is false, then this statement is false. But now here we see P is false, but Q is true. But we don't really care that what Q is, because P is false. It says if P is true, then Q must be true. But if P is false, we don't really have anything else to say about Q, so this will just be a true statement. And then same with this last one, because P is false, we don't even need to check anything, it'll be true. So the only way a conditional can be false is if this first one is true, in this case P, then the second one is false. That would be the negation of the conditional, so we would have a true and false, then it's false. And then finally we have this biconditional saying P if and only if Q, which basically means we can actually express this equivalently as P if and only if Q is the same thing. It's equivalent to saying if P then Q and if Q then P. So basically it's a conditional that works both ways. Okay? And so this is going to be true if the truth values are the same. So basically we can look at this first one, they're both true, so this will work. And we see that if we use this version down here, we can see this also holds, because if P then Q works, and if Q then P works. Okay, but now we go to this next one, true, false. If P, then Q would not work, because this one's true, but this one is false. So we're saying if P is true, then Q must be true, and if Q is true, then P must be true, but in this case, this does not work, so this one would be false. And then same reasoning for this one. Now, if we just had P then Q, then this would be true, but since we have to have Q then P as well, then this one doesn't work, because when Q is true, P is not true. So this one will also be false. But when they're both false, both of these are going to be satisfied down here. P then Q, since P is false, we know it's true. And Q then P, since Q is false, we know it's true. And so since both these are true, this will be also true. And so that's kind of an intro to using logic and comparing different propositions. Okay, so now let's move into quantifiers. So this is where we have some proposition and we have to say something about the value that's going into the proposition. So in this case, this P of x is a proposition. Like an example for P of x could be like x is greater than 0. It depends on x whether it's true or false. So if x is 1, then it's true, but if x is negative 1, then it's false. And so that's what this P of x is representing. Okay, and so this first quantifier is the universal quantifier, which basically this sentence in English would be for all x, or for any x, right? For all x, P of x. So like in this case, it could be for all x, x is greater than 0. And this would be false because every value of x doesn't work. And so this statement is true. This statement will be true if P of x is true for any x value, or for every x value. Okay? And so if any x value makes this false, then this statement would be false. And so now we have this existential quantifier, meaning that in English it says there exists an x. So there exists x such that P of x. And so if we use the same example, we could say there exists x such that x is greater than 0. And this would be true because we know there is an x. We just have to show there's one x. So in this case, 1 would be an example. There exists an x such that it's greater than 0. Okay, and also there could have to be like a universe that x is in. So in this case, if we said like x is in the real numbers, we could say there exists x in the real numbers such that P of x or x is greater than 0. And so this is true if P of x is true for some x. Okay. So it doesn't have to be only one x, just any x or all x. So if this one's true, then this one will also be true, because if they work for all x's, they work for some x. Okay, but now we have this unique existential quantifier, basically saying that there exists a unique x such that P of x. Okay, so there exists a unique x such that P of x. So in this case, if we use the same example of x greater than 0, there does not exist a unique x greater than 0 because 1 is greater than 0 and 2 is greater than 0. So we have two values that are true, but this is saying that only one x is true. So this is true if P of x is true for 1x. So for one input x. Okay? So now let's briefly think about how do we negate a quantifier. So let's say we had a statement that said for all x there exists a y such that x plus y is greater than 0. And so this would be like our P of x, but in this case it's P of x and y. It depends on both of them. Let's think about how would we negate this. What if we wanted to say this is the negation of this statement? We can put a little knot here. How would we negate this through? So if we wanted to show a negation, we would have to show that not for all of x there does not exist a y such that this is not true. So what would that mean? So the negation of a for all x would be that there must exist an x such that the rest of it is not true. So this one would become an existent x, and this one would be not the rest of the statement. Okay? And so if we exist x such that not the rest of this, we have to show that there does not exist a y that satisfies this equation. So if there does not exist a y such that this is true, then for all y's this is false. So we have a for all y this is false. And so now we can move the not into here. And now we just need the negation of this negation of this proposition, which simply would be that since x plus y is greater than 0, we could say x plus y is less than or equal to 0. Alright, now let's move into sets. And we're going to start by talking about different, already known sets of numbers that you might come across. So first we have the natural numbers, denoted by this script n. And so the natural numbers are basically just 1, 2, 3, 4, and all the whole numbers going to infinity. And so in some contexts, you might use 0 included in natural numbers, but in most cases, natural numbers are 1, 2, and all the way up into infinity. Okay? And then the integers, denoted by this script z, is basically all whole numbers. So we could have from negative infinity, and then we go up, it includes 0, 1, 2, and goes on. And so that's all the whole numbers. Okay, so now let's move into the rational numbers. The rational numbers are denoted by this q, and so this is a set of all numbers that can be expressed as a fraction of two integers. So just to give some examples, obviously all the integers can be expressed as a fraction of two integers because it can be just the number over 1. So we could just have any integer, just to name a couple random integers. And then we can also have any fractions of numbers. And then these can also be infinitely repeating, or whole numbers. That's also just 2. So really anything that can be expressed as a fraction. So you could write decimals because those can be expressed as fractions, right? So these are all the rational numbers. And you could write this a bit more formally, saying it's a number that can be expressed as a over b, such that a and b are integers, and then obviously b cannot equal 0, to give a little bit more of a formal definition of a rational number. Okay? And so now we have any real numbers. So the real numbers include all of the rational numbers and irrational numbers. So we could have the same thing, things that are expressed as fractions, or we could have also irrational numbers like pi or e, or the square root of 2, or 0. These are really just any numbers that you can think of that you would use. Rational, irrational, anything. Okay? And then finally, the complex numbers are all the real numbers and numbers with imaginary parts. And so we could obviously just have any real number that we showed before, but we can also have numbers with I in it. Or we could just have just I, or we could have negative 5 plus 2i, just to name a couple random ones. And a more formal definition of this would be a plus bi, where a and b are in the real numbers. Okay, and so we won't go into too much detail on these sets, but these are just some common sets you might see. More often probably integers or real numbers, or maybe natural numbers when you're dealing with problems. Okay, and so now let's get into some set theory and how we can use these sets or any set of numbers that we want. So first off, what does it mean to be a set? So there's a few ways we could define a set. And one way is simply just writing the elements that are in a set. So we could say we could have a finite set of just a few numbers. And this would be a set. And this set just has these 4 elements in it, A. But we could also write a set with a condition that it has to satisfy. So we could have a set that's the set of x such that it satisfies some proposition p of x. And so an example you might see of this could be a equals the set of x in the real numbers such that, which is usually with this line, sometimes a colon is used here, such that some proposition like x is greater than 1. And so now we have the set of x greater than 1. Okay? And so we can use this, and you've probably seen this in like an algebra class when we're defining like interval notation or set notation. So if we had an interval from, let's say, a to b, we can also define this as a set, and if we're like in the real numbers, we could have x in the real numbers such that a is less than x, which is less than b. And so we have this set notation for this interval. And so now you can see where the set notation comes from. And if you have this bracket interval, you can also denote this in the set of x in the real numbers such that a is less than or equal to x, which is less than or equal to b. And so we can define this interval as a set. Okay? And so you see me using this little element symbol here, this little e, and this basically is saying that something is in a set. So we could have an element, if we said like x is an element of a, we would be saying x is in a. And then we could also say x is not an element of a by putting a slash through it, and we would say x is not in a. And so an example, if we use this a up here, right, we could say like 1 is an element of a, 2 is an element of a, but 5 is not an element of a for this example up here. Okay? So these are some very basic what a set is. Because you'll find that really everything in math is just a sum set. Like a function is just a set of points. Or like an interval is just a set of points. Or a set of numbers, right? So a lot of things can be expressed as a set, so it's important to understand what this kind of notation means. Okay, so now let's talk about what a subset is. So we could say that if we said A and B are sets, we could say B is a subset of A if, to use our quantifiers we just learned about, for every value of x in A, in B, then x is in A. So basically what this means is for every element in B, it's also in A. So an example would be like the set of 1, 2 is a subset of 1, 2, 3. Or like the natural numbers is a subset of the integers. Or like the real numbers is a subset of the complex numbers, to use some of the number sets that we learned about earlier. And so using this subset notation with a line under is indicating that like the sets that are equal to each other, which are sets with the same exact elements, is also a subset of itself. Right? Because we're just saying every element of B is in A. In this case, every element of B is in A, so they're the same. But you could also see this notation as like a proper subset, which might be just using this kind of subset line here. And so in this case, this would not be a proper subset because they equal. And so this would not be a proper subset. And sometimes you'll see this notation as like the subset with a line through it saying it is not the same. So it kind of depends on the the situation you're in, which notation is being used. But typically if the line is here, they can be equal, and if not, it's denoted as a proper subset. Okay? And so a few other things. An example of something that's like not a subset, like if you had the reverse of the first example, this would not be a subset of 1, 2, because 3 is not in 1, 2. Now we can also define this symbol right here as the empty set, which is just the set of no elements. And the empty set is a subset of any set. Okay? Because every element in the empty set is in the subset, the set that we're saying it's a subset of, because there's no elements in the empty set. So of course it has to satisfy this proposition up here because there's no elements to even check. Now sets can also have sets within them. So we could have a set of, let's say, 1, 2, and the set of 1, 2. So now we have a set within a set. Okay? And a common example of this is something that we call the power set. So if we took the power set, denoted as usually as P sub with like the set within it. Okay? Or sometimes it's like 2 to the set because the number of elements is 2 to the number of elements in the set's power. Okay? And this is the set of all subsets of that set. So the set of all subsets of this case B. Sets of B. So to give an example, if we had B equaling the set of 1, 2, then the power set of B would be all the subsets that we could possibly make of B. And so we just said that the empty set is a subset of any set, so that'll be in there. And then we need the set of 1, the set of 2, and the set of 1, 2. And so this would be the power set of B, and notice B has 2 elements, and 2 to the 2 is 4, so the power set will have 4 elements. Alright, now let's discuss some unions and intersections. So let's let A and B be sets. Okay, let's let A and B be sets. Let's first talk about the union. So the union, which is denoted at this little u here, is, to give it in set notation, is every element x that is either in A or in B. Okay, so this is every element in X and B combined. Okay, now the intersection with this kind of upside down U is every element that's in X and is in B, or every element that's in A and in B. Okay, so let's give an example here. Like, let's say A equals the set of 1, 2, and 3. And let's say B equals the set 1, 4, and 5. Okay, the union of these sets, A union B, is going to be everything in these two sets. So 1 is in both of them, or 1 is in both of them, 2 is in A, 3 is in A, 4 is in B, 5 is in B. So the union is when both of them. Okay, but the intersection, it must be in both the sets to be in the intersection, because it's like where the sets overlap, like where they intersect each other. And we see the only element that's in both of them is 1, so the union, the intersection would just be the set of 1. Okay? And so you likely have seen this union, at least. When you're talking about an interval, you might see like the interval from 1 to 2, union the interval from 3 to 4. And so this union, since these two, as we looked at before, are just sets, the union is taking both of these sets together. Alright, so now let's talk about complements of sets. So if we let A be a set that is a subset of some universe, okay? So basically what this universe means, like the universe could be the real numbers, and A could be like just for an example, we could see like A equals 1, 2, and the universe could be equal to like the real numbers. Okay? A complement, or A with a little c up here, equals basically everything in the universe that's not in A. So it's X in the universe that's not in A. So for an example that will be a little easier to write out, if we say, let's let X be a subset of the real numbers, so our universe we're dealing with is real numbers, and let's let A equal the interval 1, 2, inclusive. A complement would be everything that's not 1, 2. So to use interval notation, we would have -infinity to 1, union 2 to infinity. And so that would be the complement. Okay? And now we could also have this set difference, which is similar to a complement. So the set difference is kind of what it sounds like. It's basically like subtracting the elements out of a set. So if we had like A using this backslash b, it's like a minus b to say. Okay, so it's everything in a such that x is not in b. And so the complement is kind of like a set difference, because it's kind of like saying everything in the universe that's not in some set equals the complement, given that A is a subset of that universe, right? Okay, and so an easy way or a nice way to picture this is using some some pictures. So let's say we had like a big rectangle that represents the universe that these sets are in. We could have like a set A and a set B, and let's say they share some elements. This is A, this is B. Right here in between would be A union B, because it's only the elements that are shared between them. And then everything that is included in here and the intersection, this is A union B. This is intersection. I don't know if I said that. So this would be the intersection. Now we could also use a kind of diagram to represent a complement. So in this case, let's just take one set and its universe. Like we have the set A, and then everything outside of A that's in the universe is a complement. Okay, the last thing that we'll talk about is the Cartesian product of sets. So let's let A and B be sets. A cross B is equal to the set of pairs A and B, okay, such that A is in A and B is in B. Okay, so an example, if we had like the set of 1, 2 cross the set of 3, 4, it would equal the set of pairs 1, 3, 1, 4, 2, 3, and 2, 4. Okay, that's everything that I got for this video. Again, this is not a comprehensive description of everything you would need to know for set theory or logic or quantifiers, but more of just an overview, so that if you see any of these notation in questions, that you can understand what they mean, because there's a lot of times you use these and you don't actually know where they come from. I also wanted to make this because I'm going to be kind of releasing some fun proofs over the next month or two. So I might use some of this notation, so I wanted to make just an overview video of notation that you should know to do some very intro proofs, so this could be useful for those as well. So I hope you found this interesting. Leave your questions down below, and I'll see you in the next one.